Do you think the abstract has a doubt sentence? If it does, there is a doubt sentence.
Second one.
I also think it's the second one. So this is what the current study intends to address. So let's see if indeed this study is able to fill this gap.
Yeah, before we maybe show the answer. Everyone finished reading? Which part you don't like it? Which part you don't like in this? Which part you like it? Think about it, yeah. Everyone in this room, half of analysts in this room are writing an abstract now, right, for your manuscript.
I think the sentence starts with IDE rates as well. It's not necessary, unnecessary. The only important thing is IED is sparsity and irregularly. So I think that something is not
Too detailed. Okay. So Hyungjun don't like that, it's too technical. And yeah, what do you think? Is there any part you hate or you love? If you write the manuscript, is there anything you can borrow the idea? Any word looks fancy or some new word you never used before? I don't know. Have you heard about this word? What is that? Have you heard? Anyone who understands that one? What is the meaning of ambulatory? 걸어 다닐 수 있는?
These
what? What is the meaning of ambulatory?
the participants here are not controlled. Like they are free to do irregular activity.
So, okay. So, what is the genre here?
Class computation.
What do you think? Cross computational biology, target people are medical doctor or us? Do you think that kind of choice of word, you like it? I know it looks very fancy, looks professional, but anyway, at that sentence, you lose, at least in this room, 100% people. And when you choose the word, you have to be carefully thinking. You want to show up, or you want to make the people understand what you want. Okay? So, in particular, you're in the senior level of the PhD. When you read the abstract, if there is something word you don't understand, then something is wrong. Okay. Okay, yeah, let's move on.
So we all know that a lot of physiological processes signals are cyclic. So of course we have the circadian rhythm present in hormones like cortisol and melatonin. We also know that reproductive hormones such as progesterone and estrogen are cyclic. And as mentioned in the abstract, um, these IED rays, which are associated with seizures, so these are inter-epileptical epileptical discharge or abnormal um, um, electrical signals from the brain in between seizures. And literature has shown that this has multi-day cycle. Now, the cyclicity of signals can be detected with numerous methods. So, for instance, um, given this data here, mm, one method which could be used to detect a signal is the fast Fourier transform. So, what we can see on the right panel um, are the strong frequencies or significant frequencies detected by FFT from the data set on the left side. So the first peak there happens at frequency 5. So it just says that in that time span of 1 second, we can see 5 oscillations. And we also have in here frequency, uh, or we have a peak detected at that's about 50 hertz. So it just says that if we are going to look at the data there, we can also see 50 oscillations in the span of 1 second. Another common method which is used to detect a cycle is autocorrelation, which tells how close a signal is from an original signal if of course the signal is moved. So in here, we can see a peak at around 0.5, and we can see in the original, and here in the data, that there is indeed a cycle of length about 0.5.
Okay. In this room, who knows the autocorrelation? Hand up? Yeah, please, hands up. Who know? Who don't know? Okay, can you explain what is autocorrelation?
So I think autocorrelation, so this one describes how 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 likely or uh,
When you have to say how to calculate the autocorrelation.
uh, so I think what we understand is if we're going to check, so let's say move 25 seconds in time. Um, so how we the property here is how likely it, how closely it resembles the
How do you
property.
calculate how close you can work?
Uh,
No abstract word. Mathematically. Anyone?
I think I did not look at the formula how to compute for the autocorrelation.
Anyone?
Compute correlation. So let's say this is x. Then we compute the correlation between xt and xt plus and time t.
So, yeah, you can say it's correlation or yeah, one way, kind of very simple way is you have this data, just copy the data. What is the inner product between these two data? What is that? Same data. So, inner product should be 1. Right? At the beginning, 1. But now I copy the data, I shift 1 data point. Okay, now here starting point is this, but now starting point becomes this. So we have this data, we shifting 1 part. And correlation is now 1 or slightly decreased. It should be decreased. Decreased. Now let me keep shift. And what happens? Compared to the 1 relationship or inner product will be decreasing. So that it's very natural to keep decreasing. Agree? But at some point, suddenly, it becomes increasing. How this happen? And in particular, it becomes local maximum here. When this local maximum can happen? If we shift this, so that this maximum locates in here, then it becomes similar. That's the when autocorrelation becomes max again. And can we say this is period? Does that make sense? Okay. So, but of course, you can see that here the 1, here. Of course, this interval will not be perfect, right? So that we use the feeding to here, and then by using this trend, we can get the information for the period. Okay. So actually, calculating a period, if you have a perfect sine function, it's a middle school problem, right? So now let's look at that data. Is it easy? In real life, actually calculating a period is not that easy. But if we use autocorrelation, we can get the good period. Make sense? Any question? Happy? Okay.
However, these methods, like most others, require, as you can see on the left side, dense and regularly sampled data. So, what if the data is not regularly sampled, or what if the data is sparse? Then what methods could be applied to detect cycling? So the current study proposes a method which works by decomposing a certain cyclic signal into 3 components. One oscillation, a polynomial trend, and a noise. Specifically, this is how the workflow of the method is. Given the data, right there, we apply the method in order to obtain the oscillations, the polynomial trend from the data. And then using these two, the underlying signal is reconstructed. To be more specific, suppose we have this data. The data points here are the black dots here. And suppose that we only take these observations. So let's consider so-called the sampling vector, which is associated to the data taken. So we use 1 if the data is included in the sample and 0 otherwise. So we call the set of observations yi's y. And then this portion here represents the oscillation from the signal. So the oscillation was written or is written as a product of the sampling vector, the oscillation basis. In here, they're using oscillation bases that are entirely cosine functions. And then we have x here representing the oscillation coefficients. And for the polynomial trend, the polynomial trend is written as a product of the sampling vector, the polynomial basis, which is the van der Waals basis.
Brenda, can you explain one more time? What do you mean let's begin all the left side first. What is the meaning of observation?
So the observations, these are the data points. And then from the data points, we can associate the so-called sampling vector, which has 1 or 0.
What is that sampling vector?
So it associates, so if a certain data is included in the, uh, if a certain value is included in the data, then we use 1 to denote it. But if the next value is not included in the data, then it is denoted as 0. This one is 0. And that's about the sampling vector.
Alright, then in the middle part, sampling vector is a vector column. Next one is matrix. And the next one is vector. Can we calculate that? You understand how the calculation is happening?
Uh,
Anyone?
this the sampling vector is converted.
And everyone, if you don't understand something, you should stop it rather than just move forward. Anyone who understands the calculation.
I think
Well,
the sampling vector
mm,
contains elements.
yes.
So the p n by e should be equal to n by 1. And
Yeah, Lisa, can you explain? I know it's a simple linear graph, but please. It's important.
since the sampling vector is there, we how to say it? I think um,
So anyway, if we do this calculation, we have a vector. What kind of vector? N by one vector. But if sampling vector here, what happens? Yeah, you're correct. These are just go ahead. It's element wise,
I
right?
think this n means the
N by one, right?
n by 1
Then
these time points means there is n time points
you
of
have
the data. And so I think this oscillation basis should be the shape of n by n.
uh-huh.
So
But unfortunately, oscillation basis should be n by n. How can we do it? So, let's think about it. Come on. N by 1 is an actual observation. Let's say we have about 100 data points. That's our actual observation. But oscillation coefficient n by 1, n should be longer than m. Because we don't assume the skipping of the data set. With a longer vector than n. Anyway, we have some basis, so basis times coefficient will be. So basically, this is first basis, second basis. The column will be. You should keep thinking. First basis, second basis, third basis. We have n basis, and then we have n coefficient. What is the meaning of this? We have n basis, and then we do the weighted sum of this n basis using the coefficient. Then the resulting will be what? Just n by 1 matrix. Okay? Which is long. Because we assume that there is any jump or not. No. Why do we put, maybe we can think, oh, maybe if there is jump, we can just using that removed thing as a basis. But can you imagine that kind of basis? When you say the oscillatory basis, what is the typical thing you can imagine? Sine function, cosine function. But can you imagine? So, this can be basis, right? But can you imagine? Can it be the basis? Of course, someone can make it, but it's very unnatural. Every basis should be sine or cosine that we can make a orthogonal, isn't it? Okay, but our data set actually looks like this. We cannot measure something. What can we do? So that in total, this much is m. But our basis length is n. Agree? Up to here is okay? So that our observation is how many points? M points. But the M point is observed in the n sizes typical basis. Happy? Then up to here is happy. We have some cosine x, cosine 2x, sine x. And then we combine it, we can generate the n-pointed timeseries data. So now this makes sense. M by n times m by 1 will be m. But we say that, oh, the sampling looks like this. But this is matrix. Using this number, can you make a matrix? Where? Yeah. Put it to the diagonal. That's element-wise calculation, isn't it? If we put 1 at the first diagonal, what that means? We will keep the first vector. If we put a 0 at the second diagonal, that means we will kill the second part. Something like that. Okay, do you get the point? So we will generate using the typical basis, we'll generate the typical vector, but our data is unfortunately observed only part of the data. We will eliminate some part using that sampling. Kind of that sampling vector is correct, but we'll put that sampling vector as diagonal. So that this is quite misleading, isn't it? If you are the order, what is the better way to here? We'll put the matrix here, and then sampling vector at the diagonal direction. Then it would be random. Make sense? Okay? Random. When you read a paper, kind of if you just understand the paper in the text, then no progress. So how to do is, you should really think, put some actual number, and then thinking about how it's really actually calculated is going on. So it's the same for everyone. If you read a paper just in a text, you never understand it. let me give you an example. In this group, what is the quadratic formula for the second order polynomial? Let me do it in Korean. 2a분의 minus b plus minus square root of b square minus 4ac. That's a quadratic formula, right? Is there anyone who don't know that formula? Okay, let's go to the middle school. In the textbook, you show that formula, and then you memorize it. Do you understand it? No. What do we have to do? We really write down the 2x squared minus 3x plus 2, and then plug the ABC into that formula. Then finally we understand the formula. Same for the advanced math as well. When you see any equation, you should plug the number. Okay, the first part, everyone happy? And then second part, thinking about by yourself. What is the meaning of that? Can you imagine? Someone thinking about it, that's what you learned at the last class. Can you imagine what's the second part? So, we want to generate this kind of polynomial in the family. So there will be various polynomial, maybe 1, 0, 0, 0 will be constant function. 0, 1, 0, 0 will be what? Y equal x 0, 0 x squared 0, 0. That is one way, but as we know that is a stupid way in the linear algebra, right? Because I know 1x, x squared are happy for us, but they are not orthogonal each other, right? So there are Legendre polynomial thing exists, right? So that we can put the Legendre polynomial here, and then here we some coefficient. Then basically using the Legendre polynomial, we can make whatever polynomial trend, right? So basically here we have a Fourier basis. Here we have Legendre basis, so that doing it, what we can do, just with these two, oscillation plus polynomial, using the sampling, we will remove some part. To be frankly, is there any difficulty in here? Here, did you learn at the second year linear algebra or not? You learn it, right? You run it. The only thing they add is this symmetry. Removing the subplot. How easy to write the paper, isn't it? Is there any serious thing here? Actually, I don't know what the next step is, to be frankly. My imagination is now they will calculate just minimize error. Am I correct? Is it difficult? How to handle the sparse data? They just make the regular trend and then remove the sparse points. Can you move? Next step is noise.
Yeah, that's
Okay.
exactly what we did.
So they add some noise. And then what do you want to do? You want to find the coefficient to minimize the error. That's a linear regression, isn't it?
So, that is exactly what they in this paper. So they indeed compute for the oscillation coefficients and the polynomial coefficients by minimizing the error between the observed data and the approximation. And they also limited the values for the magnitude of the polynomial coefficients because according to the authors, they want to capture the significant oscillations, but wouldn't want to include all those low amplitude oscillations. That's why they have been limiting the one norm of x.
Anyway, this is the key idea, right?
Yes.
Everyone now understands what they are doing. Easy or difficult? But anyway, but I love it. Now let's think about it. Now we find the coefficient. I think the basis will be fixed. I think we cannot use an infinite number of bases. They will use some, like a free coefficient. We cannot go all the way down, maybe sine x to the maybe sine 20x. And then polynomial, Legendre polynomial maybe up to some 20 or 30 or 40 until like the fitting is going on. So we have a coefficient on. Then if we calculate this side, what you will get? Which we will get some time series data which is most similar to the left side. And what is the good thing of this? If we eliminate this matrix, what we will get? In this case, we didn't know what it is. We didn't observe it. But if we remove this sampling, we already have a coefficient, right? What do we have? We have a full time series without the missing. Basically, recovered data will look like this. Here will be most similar. And plus something looks very natural. Do you like it? Well, we can basically missing the missing part as well. We can get further, not only the approximation. But this is true under the what kind of assumption? This data set is under the spaces which is 10 by 1. Kind of only oscillation plus polynomial basis, then we are happy. To be frank, let's think about it. Oscillation plus polynomial. Any other shape can you imagine? Shingo, you haven't handled so many data sets, right? Have you experienced any data which can be beyond the polynomial plus oscillation? Beyond, kind of which we cannot cover. Kind of course, like an exponential function plus oscillation will be different. But let's think about it. We cannot observe an exponential function forever. For the finite domain, exponential function will be just high order polynomial, is it? What about Sokhan? Who got admission from USA? Tell me something. By the way, everyone know about that news? Sokhan got the admission from Wisconsin. Yeah, let's congrats. So let's show the Wisconsin's power. Can you imagine something? I think their smart says this as well. They separate the time series to the oscillation plus polynomial. Because in real life, majority will be explained in this way. Okay? Of course, there will be some error, but does it matter for us? Okay? So, in this method, I think this is everything today, isn't it? Now they will apply to the something, right? So now you need to just understand this one, then that's all. What do we have to learn from this paper? Number one technique, for some certain time series data, typically, it can be separated to the which one? Oscillation and polynomial. Why we separate in this way is oscillation field has a good basis. What is that? Free basis. Polynomial, do we have a good basis? Yes. Now, of course, you can think about like a log function thing, but if we have a various log function, can you imagine any good basis function? Do we learn that kind of thing in the linear algebra? No. So these two are most natural to class. Okay, the first good idea is we can express typical time series as a two-time. oscillation plus polynomial, increasing or decreasing or whatever, or polynomial fluctuation. Happy? And then second idea is what? Their data has sparsity. So that they're using the sampling function, remove the unobserved part, and then we only calculate the error for which part? Only observed part. Very frankly, it's just really fancy term. What can we express? After express, and then when we calculate the error, where we will calculate the error? Only observed part. This is that expression in a linear algebra. That's all. But by using this, it looks something. Is it? If they don't put this one, I think it will be rejected. They may think that it's undergraduate student paper. But by putting the sampling term, it looks like fancy, isn't it? So, but what do you think? It's simple, but it's useful. Right? Useful. Good. Let's move on.
And then the authors just added a process in order to simplify the computation for X and Z. So they called this, so they eliminated, they first eliminated Z in here. In order to just minimize X, and then the optimized value of X is then used to obtain Z. The derivation for this process they have put in the supplementary sections. Here, B plus denotes the inverse of P transpose B if this exists, multiplied by the transpose.
Brenda, by the way, we only put the regularization for the only X, not the Z.
Yes.
Oh, this seems so surprising.
They
We allow the Z coefficient as much as possible.
Yeah, they did not put any restriction there, only on X.
왜 그런가 잘 모르겠다.
저기에서 보고자 하는 바는 오실레이션 비결을 보고자 하는데 아까 설명해 주셨는데 주기가 큰 그런 오실레이션 같은 경우에 진폭이 크거나 그 트렌드를 반영을 해서 진폭이 크게 되는 거 나서리가 저거를 리스트릭션을 주고 사실 그런 트렌드는 끌리는
트렌드를
게
다
있어서 캡처를 할 수 있겠다.
Anyway, please note that we only give a restriction for the X, not the Z. That's also something very clever idea. What is the meaning of this? One norm of X is less than, let's say, 10. What is the meaning of that? What is the one norm? Come on. What is one norm? Just sum, right? The sum of the absolute value of this coefficient we want to make less than 10. So that means we don't want to put too many in for the oscillation part. I think that's their intention. And Isaac's idea is if we allow the too many coefficients there to fit because the Fourier series also can fit to the polynomial trend, right? But we don't want to use the Fourier coefficient for the polynomial trend. We want to focusing on the oscillation part of the oscillation basis. I think that's their intention. Okay.
So with this process, they apply the method to different time series data. They started with a simulated time series. Okay. And then they consider taking 5 random samples per day, a total of 1,800 samples. And then they applied the method and obtained this corresponding peaks. So there are small peaks here. At 5 here, around day 30. And using these cycles detected, they're able to, and of course, the polynomial trend, they did not show the values obtained for this one. So they only showed the associated frequency for the oscillations. So again, using this and the polynomial trend obtained, we're able to reconstruct the signal. So in here, the gray part, that is the raw data, and the orange one is the reconstructed signal. Which,
It's good. Anyway, the fitting is good, but I don't understand how they get this one. So this is a fast Fourier transform frequency domain actually. Okay. How they got this? Sorry. This is coefficient of the basis.
no,
No, this is a
So-
power spectrum. Right?
yes,
So how can they obtain this? From this data we can, right? Because it's irregular sample. Irregular sample we cannot do the Fourier transform. We can't. Fourier spectrum only can be regular sample data. But here, what we do first? Yeah, go ahead.
So first they, as mentioned earlier, they first computed for Z, for X and Z. So when we're able to compute it, we're able to form
Go
this
ahead, yeah.
function. And then from there, we're able to identify the cycles.
Oh,
And
that's my question. How that number comes from?
the exact process on how it was, I did not think more about it.
Anyone, any idea? It's not that difficult. For the fast Fourier transform, what we need? Regular time series. Do you have a regular time series now or not? Where it is? Gray is not the regular time series, but come on, what? Yeah, reconstructed orange data set is regular or not? Regular. So that process should be opposite. From here, we got this orange time series first, using all that coefficient. The good thing of orange time series is every regular time we have something. And can we apply the Fourier transform? Yes, then we can get this power spectrum. Brenda, when you give an introduction, what was the introduction motivation for this study? Autocorrelation, power spectrum cannot be calculated because of what? Data is irregular. That's what you tell. And here, what do you have to explain? We got the regular data first. You get it? Mm-hmm.
Okay. So that is how they were able to construct the power spectrum for the method. Um, but we also would like to compare the result of this one with other methods. So for this, the authors considered CWT as comparison. So for CWT, as you can see, this one makes use of dense sample, about 26,000, compared to BPWT, which only makes use of 1,800 samples. But even that is the case, if we compare the power spectrum for the CWT and BPWT, we can see that the current method has good alignment with the peaks of CWT. So since the authors consider the performance of the method using simulated time series data, and the next step they tried was to see how this method performed with real world data. So here is a data for the IED data for a patient. And then from there, or from this one, random 5 random samples per day are taken. And so the authors wanted to see whether the reconstructed signal using only these 1,800 data points would be close to the original data. So as you can see from here, there's also a good alignment of the power spectrum for the current method, which uses again dense data compared to the CWT. And we have the following reconstruction shown here. But then in the abstract, the authors want to see the performance of this method when the data is sparse, or if the data is unevenly sampled. So that's why for the next step, the authors considered changing the sample density and then observing how this will impact the output of the method, the BPW. So first they considered just one random sample per day. And then again they considered the power spectrum comparison with CWT. And then gradually increased the number of samples per day. So we can see from here that if the number of samples increases, of course, trivially also, the cycle detection performance of the method becomes better. So as you can see, or shown by the close correlation or close resemblance of the power spectrum of BPWT to CWT. So, but I don't know, this might be expected, but as expected, when the density of the sample gets lower, we also see a decreasing performance for BPWT. What about data drops? So how would this affect the output of the current method? So in here, 12-day drops are considered, which means that so we have like clusters of data points taken here, and then for the next 12 days, there are no data point taken. And then after that, we again have this group of data points. So if 12-day drops is taken as a characteristic of the data, then we can see here the power spectrum from DPWP. Well, this still has peaks, significant peaks aligning with the CWP. But as we gradually increase the number of drops in the data, we can see the performance of DPWP declining. As can be seen by the not close resemblance of the power spectrum or the peaks here with CWP. So those are, I think, are just the important results in this study. So although BTWP can detect signals using sparse and irregularly sampled data, it's not that good when the density of the sample decreases and when the are long and frequent data drops. So a lot of things should still be improved with this method. Do you have questions regarding this article?
Is there any reason that the DPWP has lower performance for the longer less frequent data? Longer.
Yeah. I can only speculate because I did not really read more into it and look at the process. But maybe the reason for that is maybe it's difficult to capture the how do I say? If we're going to go back to the data files. So if the dots are that long, the method has difficulty finding and identifying the oscillations, the basis, or I mean the conditions for the oscillations. But the reason why it's having difficulty in identifying the trend, as I said, I did not read more into it.
May I have a question?
Yes.
So, could you show the previous page? Next. Page 11.
Page 11. This one.
Yeah. And next figure. And there are, so if the density becomes if the sampling rate becomes dense, the amplitude looks smaller. So is it natural?
The amplitude.
Yes. Amplitude of reconstruction. Is it natural?
Mm. Oh, you're asking why that happened?
Yeah, why?
I think
Yeah.
the total amplitude is restricted by the long number of M. So you can see the spectrum that the longer period amplitude arises when the dense sampling. So uh, low frequency oscillation basis have more amplitude, so small oscillation have low, I think.
Yeah, so it's because of the algorithm. X1 smaller than delta.
I
See, I see.
What if we release that regularization threshold? What if? Do you have any idea? No idea.
Is there any process to determine the delta for the longer basis?
As I have understood, in order for them to determine delta, they they use this 10-fold 75-25 cross validation. So it's like they took 75% of the data, they use it for training, and then the remaining 25% they use it for testing. So what they did was in the testing part, so they observed the error from the prediction made by the reconstructed signal, and then the testing part. And then so they gradually um, change delta until they are satisfied with the error. That is how they obtain. Yes, we have other questions. Maybe people who are more knowledgeable in this could answer. Let's go. So Kim is asking if I have an idea what is going to happen if we release this, right? If we don't put a restriction on the one norm, I don't have an idea.
So maybe the trend could be reflected to the oscillator basis, right? Oscillator coefficient of the oscillator.
Of observation,
Yeah,
the trend of frequency.
yeah. I think so. If you release that term, the the trend of the overall time series could be reflected in the coefficient in the
It would be mistaken as another cycle. That's a different added cycle.
If you use the long period basis, then trend could be.
We have other questions. So if there are none, then thank you for listening and also thank you for to